Good afternoon. All right, so we were in the process of finding a power series given another power series. So finding one power series from another. And what we have here is the power series for minus natural log of 1 minus x. There's the power series for it. X to the k over k. It actually looks a lot like the exponential. The exponential is x to the k over k factorial. But at any rate, we want to find the power series for f knowing that power series. So we have to do a sequence of replacing, multiplying by something, whatever it takes. All right. Well, the first thing we're going to do, first thing we see, we're going to take this series over here, we're going to start doing stuff to it to try to create that function right there. So let's see what we can do. So the first thing I'm going to do is multiply by -1 because there's no -1 out there. So let's get rid of that -1. So we know that the power series for... Did we not finish the last one?
I don't think so.
All right, well, let's finish this one first, and then we'll go back. So if we multiply both sides by -1, all this does is put a minus sign out in front of the series. And we have that. So multiplying both sides by -1. Next, we need to kind of build up this x squared from this x. So what are we going to do with the x's? Replace with x squared. So substitution, composition, that kind of math. So we know that the natural log of 1 minus x squared will be found by the following power series. So we're just going to replace. I'm getting tight on space here. I'm just going to use that abbreviated notation here, which is totally fine on the test too. If you just put a 1 there, I know you mean k equals 1 to infinity. So I'm going to replace the x with x squared inside here. So this will be x to the 2k divided by k. So we're getting closer. Now the trickiest step of them all. What do we do next? How do we do that? You can't just take the square root of both sides. We don't want the square root of a power series. We want a power series. So is there a way to invoke a square root on this side?
Raise both sides by 1/2.
Do you raise it to the e?
No. Your Gage?
Multiply both by 1.
Multiply both sides by 1/2. Because if we multiply both sides by 1/2 on the log side, it does turn into a square root of 1/2. So we can't raise both sides to the 1/2 because we don't want a square root of a power series. But if we multiply both sides by 1/2, so we can do that. That's pretty easy. That just turns into a multiplicative constant on the outside. So we have that scenario. And then the final step is that, oh, this actually is f of x, right? Because we know that that 1/2 can come up and turn into a power on the inside, which is a square root. So that is our power series. This is the power series that we have been looking for here. So there is our power series, right there.
Do we have to have the constant out to the left, or is it alright if we leave it on the right side?
Are you saying, could you move it inside?
No, leave it just on the left of the summation notation.
Yeah, you can leave it on the left of the summation.
Or sorry, right of the summation.
If it's on the right of the summation, then it's inside the summation.
Oh, okay.
So either way, it can be in the summation or just out in front. Yeah, so that's kind of clever. Kind of clever. Let's just finish this slide and then we'll go step back to the prior slide, since we're in the theme of this type of thing so far. Okay, let me ask you one other question though. So this is the the interval of convergence. It's kind of like the domain for this power series here. Anytime we do a replacement, we need to check and see if the interval of convergence has changed. If we multiply by a constant, which we did in 2 places, multiplying by a constant does not change the interval of convergence. If you think about the ratio test, you may think, oh, well, if we multiply by a constant, it should shrink or grow the interval of convergence. But remember that we find the interval of convergence from the ratio test where we do an a sub k plus 1 divided by an a sub k. If we multiply by a constant, we end up multiplying both the a sub k and the a sub k plus 1 by that same constant. So when we form that ratio, those constants just cancel. So multiplying by a constant is not going to affect the interval of convergence, even though it feels like maybe it should, but it doesn't. But what does affect the interval of convergence is this thing. We replaced x with x squared, and so this may or may not, but we definitely have to check. And so here's how we've been doing it. Up here, this says that -1 is less than or equal to x is less than 1. So we replaced this x on the inside with x squared, so that means that we're going to come over to our interval of convergence and do the same thing. Replace this x with x squared and then solve that. So the solution of this, there's 2 ways. You can think about it graphically, which I showed you before. You can think about it graphically, or we can use a clever algebra technique and say, oh, this is always bigger than -1, so it really, we can just erase that. The solutions to both of these are the same, right? Because x squared is always bigger than -1. And now, if you initiate that square root of both sides, now that you're in Calc 2, I think you finally know that the square root of x squared is not x. The square root of x squared is absolute value of x. And so this tells us that our interval of convergence is that. It goes from -1 to 1, but we don't include either endpoint. So that's the clever algebra way to do it. You can also do it geometrically by thinking graphically. You think about your function. Here, we want the function x squared to be between -1 and 1. So if we take a picture of y equals x squared and draw a graph, there's 1. But we're talking about x's, so there's -1, there's 1. So we want the x's that generate a function value between -1 and 1. So the function value is on the y-axis right there. We want to be in this pink. Well, the x's that generate y values that land in that pink interval are exactly these x values right there. Right? The x values between, not including the endpoints, between -1 and 1. All those x's between -1 and 1 generate y values, x squared values, that are between -1 and 1 on the y-axis. So that's the visual geometric way to get at it. Or this is kind of a clever little algebra way. Ditch the minus thing because that's always true, so it's not adding extra solutions. And then when you take the square root of both sides, remember that the square root of x squared is not x, it's the absolute value of x. So those are the 2 ways that you can solve that little inequality. All right, let's go ahead and finish this one off. So the function on the left here, f, what's the only thing we have to deal with?
4x squared.
The 4x squared. So this is the only part we have to deal with right there. So all we do is come over to the inverse tangent, and while we're talking about inverse tangent, the 5 series that you need to know for the exam a week from today are right here on the board. The binomial, which we're going to do in a minute, e to the x, the geometric series, sine of x, and inverse tangent of x. Those are going to be the 5. So binomial, I'll write them over here too. Binomial, e to the x, the geometric series, sine x, and the inverse tangent. So those are the 5 that you will see on that exam in a week. So all we're doing then is replacing the x's in here with 4x squared. So we're going to take our series. It starts at 0. Nothing else is changing. We're just going to come in, look at the x, replace it with 4x squared. So 4x squared raised to the 2k plus 1, all divided by 2k plus 1. And the interval, we're going to have to fiddle with that. What was that?
Is that it? Really? Just chuck it in? Oh, yeah.
We're not done yet. We'll simplify it a little
Yeah,
bit,
yeah.
but yep, that's all we have to do. So we also have to do it for the interval of convergence. So there's our new interval of convergence. We'll have to simplify that. So in here, we are left with the following. All we have is a power to a power. So we're going to have this 4 out in front. That's going to be raised to the 2k plus 1. We're going to divide by 2k plus 1. And then we're going to have x to the 4k plus 2. We've got that. So the power distributes to each of the factors. Power to power, you multiply. So that's that part. And then here we have negative 1/4 less or equal x squared less or equal 1/4. And then we're in that same scenario we were in just a moment ago. We can do our kind of clever algebra technique is this. That side's always true. So it doesn't add any extra solutions there. It doesn't restrict anything. So we can just get rid of it. And then we can say, oh, let's take the square root of both sides. And we know that the square root of x squared is not x. It's the absolute value of x. So we get absolute x is less than or equal to 1/2. So that tells us that the IOC, the interval of convergence, includes the endpoints, and it's going to go from negative 1/2 to positive 1/2. That will be our answer. Gage, question?
The endpoints only change if you integrate or derivative?
So yes. So we don't have to retest. The nice thing about substitution is we don't retest endpoints. All we have to do is that simplification of the new interval, but the endpoints don't get fiddled with. We only have to recheck the endpoints if we differentiate or integrate. Yeah.
Like recheck the convergence at the endpoints?
So if you differentiate or integrate, then you have to check the convergence at the endpoints, yeah, because they could change. All right, so there was one question we had not finished over here. Oh yeah, that one. Okay, so yeah, this one's a little slightly different process. So let's talk from scratch about this. So the idea here is using derivatives or integrals as opposed to what we just did on the last slide where we were substituting and multiplying. Substituting and multiplying is way easier. So here we want to get a power series for G given this function for which we can find a power series really easily. So to build the power series for F, we have the known power series for the geometric series. We replace the x with a negative x here, so we replace the x with a negative x over on this side, which creates an alternating geometric. Interval of convergence will be the same. And then we say, okay, now let's replace x with x squared. So we're going to turn that x into an x squared, which means come in here and turn that x into an x squared. Simplify the power, exponential to exponential, multiply the exponents. And if we replace x with x squared here, we've just seen that that creates the same interval of convergence. We just did 2 like that. Last step here, now we multiply by a factor of x. in there. We also multiply by a factor of x inside the summation, so that puts an exponent of 2k plus 1. We add 1 to the exponent. And when you multiply by x, that's not going to change the interval of convergence. Let's just think about that for a minute also. Interval of convergence, you're doing that ratio. A sub k plus 1 divided by a sub k. If you look at a sub k and you look at a sub k plus 1, if one's multiplied by x, the other's multiplied by x, right? So but the difference between the powers is the same. Whether the power was 2 and 3 or 3 and 4 or k and k plus 1, the powers are still the same, so the simplification will lead to the same exact interval of convergence. So multiplying by x is not going to change the interval of convergence. Multiplying by constant doesn't change the interval of convergence. We now have a power series for f. Okay, so there's the power series for f. And we need to figure out, how do we get to g from f? If we integrate f or differentiate f, does one of those things get us to g? So what we did was say, okay, let's take the function f and let's integrate it. I put it in log form. So then when it integrated to 1/2 natural log of 1 plus x squared plus c. That's almost equal to g. Not quite there. So what are we going to do? So this tells us then that g is equal to, so we've got to try to end up with just natural log of 1 plus x squared here. Right, that's what we want to end up with. So what do we have to do to both sides to get rid? The c is no big deal, right? Because you can just add it or subtract it away.
Multiply by 2.
Multiply by 2. If we multiply both sides by 2, okay, we get a constant here, but that constant can be moved over here. So if we multiply both sides by 2 first, we're going to get 2 times the integral of x over 1 plus x squared dx. Everyone okay with that? So we multiply both sides by 2. That's going to give us g. And okay, yes, there's a constant. But if we integrate here, we're going to get a constant anyway, right? So if this constant, if to make g equal to this, there's going to be a constant that comes out of this anyway. So putting this constant on the other side, it's not going to change anything. We can imagine the constant of integration from this being combined with the constant of integration from that, or not integration, but just that constant. We just have to make sure that when we look at the left side that there is a constant there somewhere, and if we have to evaluate it, we will. But at this stage here, if we multiply by 2 and then subtract the constant, oh, there's already a constant in this integration. Right? When you integrate this indefinite integral, there's going to be a constant. So that can be the one constant on that side. So g of x is 2 times the integral of f. So this is 2 times, all right, there's f. So this is the integral of f of x dx. So if we integrate f and then double it. All right, so let's do it. So we come down here. So this is going to be 2 multiplied by the integral, indefinite integral of f. So f is this power series that starts at 0, k equals 0. We put in our switch, x to the 2k plus 1. And the interval of convergence we'll get to in a minute. We're integrating, so we're going to have to change it, possibly at the endpoints. Let me just move this interval just over here, get it out of the way. All right, so now we have to integrate this power series to get a new power series. And when you integrate, do what you always do with a polynomial. Add 1 to the exponent, divide by the new exponent. Minus 1 to the k, there's no x there, so that doesn't matter. We don't care about that switch. That switch just comes along for the ride. It's just a constant. Whenever you integrate, constants just float around. Oh, let's maybe not start at 0. Let's think about that for a minute. Okay, so we add 1 to the exponent. So we get 2k plus 2. We divide by the new exponent, so we divide by 2k plus 2. All right. And when we integrate, we always get a constant of integration. So we'll put the plus c out there now. So there's that c that we needed a constant at some point. There it is. Now let's think about what this index should start at. We saw that as we differentiated a power series, we were jacking this up by one at a time. And the concept was that if you have a polynomial and you differentiate, you're always losing a term if all terms are represented. If you have a constant term, the derivative is 0. So you lose a term. So let's see what happens here. Let's look at the smallest power on x here. When k is 0, you have an x to the 1. What is the integral of x to the 1? X squared over 2. So what we want to make sure is that whatever we start this index at, that matches. So we want the first power in our antiderivative to be a 2. And what would k start at to get the first power to be a 2? 0. So when we're integrating, we usually don't have to adjust the index at all. Usually with integration, it will just work out fine. But with derivatives of a power series, you usually have to bump it up by 1. Right? And the issue, remember, was that when you bring down the power and you subtract 1, if you have x to the negative 1, that's not a polynomial anymore. You have to make sure that your power is not negative. OK, so there is a power series for G. We can check our constant. Let's solve for C first. So G is natural log of 1 plus x squared. I'm going to actually write that here because it's going to be easier to figure out that constant if I write it like that. So we can put the G all the way out in front if you want. OK, let's just check. We know that in here, the lowest power of x is x to the 2. So when you plug in 0 here, what is all this infinite series business going to give you? If you plug in x equals 0, all of that becomes?
X squared.
Because 0 plus 0 is 1?
You're plugging in 0 for x or 0 for k?
X.
Okay.
X. So if we're trying to solve for the constant, if we plug in x equals 0 on the left, we get 0. So we want to do the same thing on the right. We want to make sure that this side and this side match with the constant. So if we plug in 0 on this side, so we're plugging in x equals 0. So if we plug in x equals 0 here, we get 0, right? Because the lowest power of x, there's no constant in the series part of it. The lowest power of x is x to the 2. So the next power after x to the 2, when at k is 1, we get x to the 4. So we have all these powers of x, and if we plug in x equals 0, the whole series becomes 0. So this is all 0. If you plug in x equals 0, so let's say that. So plug in x equals 0. So the whole reason we're doing this is to pick a c so that both sides match. So if we plug in 0 on the right, we get natural log of 1, which is 0. So that's the left side. The right side is going to be c, correct? And so that tells us that c has to be 0. So we don't need that constant after all. So our conclusion here is that therefore g of x, the power series for g of x, is just this thingy up here. So that is our power series for g. We don't need the plus c because the c turns into a 0. And that starts at 0. So there is our power series. Now we have to deal with the interval of convergence. So with differentiating or integrating, the inside of the interval does not change. It's just the endpoints. It's the goalposts. Either we include or exclude the endpoints. And so we have to test. So our interval of convergence starts at -1 to 1. So we need to test both of those. So we have to test x equals -1, and we need to test x equals +1. So we're going to test both of those into this power series. Does the 2 affect convergence? No. So we don't even have to consider the 2. Does starting at 0 or starting at 100 matter for convergence? No. You can chop off the first 5 million terms if you want, so you don't have to index this here. Up here we have to index it because we have to start at 0 to start with the power of x squared. Down here, we don't care. We don't care what the index is there. You can put it if you want, but it's not going to affect anything. So, oops, and I'm plugging in x equals -1 right there. So -1 to the 2k plus 2. Does that simplify to a single constant as opposed to a switch? Is 2k plus 2 always odd, always even, or does it change? Always even, right? 2 times any integer is, any positive integer, is going to be, I guess even negative integers can be odd or even. But so 2 times any integer is even. And if you add 2 to an even integer, you still have an even integer. So this is going to be -1 to an even power. So that's going to simplify to 1. And then in the denominator, we have this. OK, so does that infinite series of numbers converge or diverge? It's going to converge by what test?
Divergence test.
You cannot converge by the divergence test. You cannot converge by the divergence test. The divergence test.
Series going to 0.
What does the divergence test for? Divergence. So if the divergence test is inconclusive, then we do, then we have to test using something else. What kind of series is this?
Geometric.
Nope.
Alternating geometric.
Nope. I mean, one of those words was right. It's alternating. It's alternating. So first off, geometric always has a k on the outside. Right? A geometric is like 1/2 to the k, 5 to the k. It's an exponential looking item. So this is alternating. Right? We've got a switch. That's truly a switch. It's not just a switch wannabe. It is a switch. Plus, minus, plus, minus, plus, minus. So that's alternating. And in this chapter, unlike the last chapter where you have to show the alternating series step 1 and 2, here it is enough to say it's alternating and it's decreasing to 0. So it's enough just to say that this converges by alternating series test. That is totally fine. In your mind, you're thinking it's alternating and the terms are decreasing to 0, then it's going to converge. If you went through the 2 steps of the alternating series test, both would come out true. But in this chapter, all I want you to do is recognize that it's alternating, and if the limit of this is 0, that's enough. And to be thorough, you probably should say this too, but you don't have to. It's totally fine for me in this chapter. If you have an alternating series, you can just say converge by AST. Okay. Now, when x is 1, let's see what we get. So we have convergence at one endpoint. So now we're plugging in +1. Oh, +1 raised to any power is still +1. So did anything change here?
No.
Still have an alternating series. The limit of basic k is still 0. So this is going to be exactly the same. So therefore, the interval of convergence has increased. Not in radius, but it's increased by including convergence at both endpoints. Yeah?
So how did you know which function to start with?
The geometric, because that looks similar. You can just start thinking in your mind that, oh, if I peel off the x is just a multiplication. Right? And then down in the bottom, we've done a couple of examples where we replace this x with something. So it's just kind of by experience. But if you look at the power series that we've been dealing with, we basically have two types. We have the first 6 that are all based on the geometric series. So all these ones on this page stem from that. So your two kind of root power series are geometric series, which leads to the alternating geometric and all these other things. And it leads to the arctan. And then on the second page, these ones are almost all, except for the binomial series, based on E. So E and geometric series are kind of the two like scaled down series that you can build bigger series from. Okay, so let's go to Taylor series. So we've talked a ton about Taylor polynomials, and we just got through talking about power series. Now we're going to talk about Taylor series, which are a type of power series. So when you hear the expression power series, you're thinking of long polynomial that's never ending. Some people will call it an infinite polynomial because it goes forever. A Taylor series is a power series, an infinite polynomial. The one thing that distinguishes a Taylor series from just a general old power series is that a Taylor series is constructed from a function that's differentiable forever. You build it. A Taylor series we are building. Remember, Taylor polynomials, take 5 derivatives and build that whole expression. So when you hear Taylor polynomial or Taylor series, you think about a hammer and a nail. You're building it, right? You're taking all these derivatives. You're using that coefficient pattern for the coefficients, the nth derivative of a divided by n factorial or k, whatever letter you're using, right? You're building it. So a general power series, just as this infinite polynomial, the ones that come from a Taylor series are the ones that are also classified as Taylor series come from a function. You start with a function. Like if you just write down a random power series, 1 minus 100x plus 12x squared minus 1/12 x cubed, whatever. That is not going to be a power series that came from a function and its derivatives. If you randomize these coefficients, you are not going to be able to find a function that's infinitely differentiable that will build that as a Taylor series.
Didn't we already work with like functions at like approximating them by following those?
So we were looking at Taylor polynomials, so they were finite. So now what we're doing from that other section where we started with the Taylor polynomial, which created the best quadratic approximation, then the best cubic approximation, and the best quartic approximation, etc. Now all we're doing is putting plus ... on the Taylor polynomial. Right? That's all we're doing. A Taylor polynomial that never ends becomes a Taylor series. So all we do is plus ... So there is our piece of 3 right there. Put plus ... Now it's a Taylor series. So this same pattern with the coefficients continues forever. Now we've created a power series from a function. That's called the Taylor series. It's just one type of power series. If you have a Taylor series that happens to be centered at the origin, they call it a Maclaurin series.
Is there a reason for that?
There must be. And I was talking to my son, I think it was last year, and he's like, why does Maclaurin get all this credit for the series that's just centered at 0? There must be a reason, but I don't know what it is. I was like, that's a good question. He felt like he's getting a lot of credit when Taylor's the one that did all the work, and then this one gets his name if it has a center of 0. The simplest Taylor series is called the Maclaurin series. There's got to be a reason, and I keep wanting to look it
Who
up.
is this Taylor guy?
Who's this Maclaurin guy? Taylor guy, we know what he's doing. He's doing all sorts of approximations. Okay, so here's a subtlety that when you get into advanced calculus, if you go that far, you wrestle with this. So it says, for a Taylor series to be useful, we need to know a couple of things. So we need to know where it converges. So that's the interval of convergence. And we also need to know the values of x for which the Taylor series is identically equal to the function. When we look at our list of series here, we see, okay, some of the intervals of convergence are not all reals, right? Lots of these intervals are just subsets of the real line, not the entire real line. Over here, most of them are the real line. So that's the first thing. We need to know where they converge. We need to know their interval of convergence. That's the first thing. Now the second thing is way more subtle. For all the functions that we deal with, the Taylor series and the function are going to be identical on the interval of convergence. Okay, they're going to match. There is this weird subtlety, though, that you can, just because you've created a power series from a function, it's not necessary that that Taylor series actually is equal to that function. Like there's a separate step that you have to show that those are actually equal. Now we can believe it because we've looked at how you keep building and you get better and better approximations, so conceptually it makes sense. And 99% of the time the Taylor series is equal to the function. But you can always build weird things in math. It is possible, usually by using piecewise defined functions, it is possible to use a piecewise defined function that has a Taylor series that is not equal to the original function. It is possible. But for us with common functions that are not piecewise defined, e to the x, sine x, hyperbolic cos, all those common functions, you start taking derivatives and building the Taylor series, it's going to equal the function.
Wow, absolute value of x.
Absolute value of x is a piecewise defined function, so that's not in this conversation. No piecewise defined functions. So that is going to be a topic for an advanced calculus class to wrestle with this. For us, dealing with common functions, the Taylor series and the function are equal. Okay, for all the common functions.
What's that advanced calculus class called?
Advanced calculus.
Really?
If you go on in math,
There's only one advanced calculus class?
yeah. So at CU they call it advanced calculus. Some schools will call it analysis.
Okay.
And then there's real analysis 1, which is considered regular advanced calculus. Then there's real analysis 2, advanced calculus 2. And then there's complex analysis 1, and then complex analysis 2. So if you go on and do a ton of math, then those analysis classes are proof classes, where you have to basically go back to the calculus book to the very beginning and you prove every single theorem in gory detail. It takes a unique individual.
Fun.
Yeah, winning, not. Okay. Yeah, it's often considered the hardest class in an undergraduate math degree is that analysis class. Usually considered the hardest class.
Nice.
The gauntlet,
Nice and second.
right? All right, so let's take a look here. So we've seen already that if we have a power series, we can build other power series. Kind of like viruses. If you've got one, you can build all these other ones by doing things to it. Add a little water, throw a little salt on it, whatever. You can build other power series from a known power series. You can do stuff to it. Now, those are especially easy to work with when they're truly Maclaurin series. When they're centered at 0, you can move stuff around really easily. In this class, if we are asked to find a power series centered at the origin, most of the time it means take one of these guys and do something to it. differentiate it, integrate it, multiply it by power of x, multiply it by a constant. But when you see this type of thing where the center is not the origin, 99% of the time it means break out the hammer and nails. We've got to start taking derivatives and we need to build this Taylor series. Okay, so if the center is not 0, you should be thinking, oh, take a ton of derivatives. Plug in the center. Build it. Okay?
Is that the same thought process for functions that are undefined at x equals 0?
What do you mean? If the function is undefined, say that again.
If the function is undefined at x equals 0 and it's not
Oh.
a tangent,
So if the function is undefined at 0, then you can't build a Maclaurin series for it
okay.
because it's not defined at 0.
But you can build a Taylor series.
We can build the Taylor series,
Yep.
but if we don't center it at 0. So
Yeah.
we're going to center it just a little off.
Okay.
We're going to say, okay, we can't center this series at 0 because division by 0 is undefined. So if we see a function that has division by 0 at 0, then we definitely know that we have to create a series that starts somewhere else, that has a center somewhere else, which means non-Maclaurin series, which means start taking derivatives.
So there is no
Yeah.
Maclaurin series for something like x sine 1 over x.
What about x on 1 over x?
It goes like this, then it,
The bow tie function?
yeah.
What about it?
There's no, it's undefined in the
It's
center.
undefined
so
at
you
0,
can't-
yes. X sine 1 over x is undefined at 0, so we can't build a Maclaurin series for it. That's right. Okay, so let's make sure we see what it's saying. So it says, write the power series in summation notation, find the interval of convergence, and it says 4 non-zero terms. So they're going to tell us, on the test you'll be told, how many non-zero terms you want to create. Now this has one thing that we're going to do here that we are not going to do on the test that I'll point out as we get through this. So first off, it's usually easier to use y's, and we don't have to deal with the of x piece, and it's usually easier to write it like that. So there is the function, the 0th derivative. So it said that we wanted 4 terms, so we're just going to start differentiating. And none of these terms are ever equal to 0 at 1, so no big deal. We just have to go down to the 3rd derivative. So we're going to differentiate all the way down until we get to the 3rd derivative. And I guess I should make sure, my memory of reading the instructions is that it said 4 non-zero terms. But if it said 4th order, then I'd have to go out one more derivative. But it says 4 non-zero terms. So that's going to be the constant, power 1, power 2, power 3. So we only have to go to the 3rd derivative. 3rd derivative. Okay, we can multiply and get negative 24, x to the negative 5. Now we evaluate. So keeping track of everything. Now we're going to evaluate the function and its derivatives at the center. So that's going to be a 1. And then y prime of 1 is going to be -2. Y double prime of 1 is going to be 6. Y triple prime of 1 will be negative 24. Okay. So this is what we did when we were building Taylor polynomials. So now we're going to build. So we're building a Taylor series now, so I'm going to call it T of x. Back in the other section, we would call it P sub 4 if we were only going out to order 4, P sub 3 out to order 3, whatever. Here we're going all the way, so we're going to call it T of x Taylor series. So it starts with 1 minus 2 times x minus the center to the 1 plus 6 times x minus the center to the 2 divided by
2 factorial.
2 factorial minus 24 times x minus the center to the 3rd divided by 3 factorial, and then plus ... That tells me you know it's a series. If you don't put the plus dot dot dot, then you're finding p sub 3. So make sure if it's asking for a Taylor series that you give a series. So there's got to be a plus dot 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 in the expanded form. Okay, so there is our Taylor series. If we are asked to find the radius of convergence, we would want to use the ratio test, or the root test possibly. But the only way to use the root of the ratio test is to have this in summation notation. We would have to turn this into its closed form. Right now it's in its expanded form. We'd have to put it in its closed form. We would have to write it as summation. That is the piece I will not ask you to do on the exam. Creating the summation notation from an expanded series is not light work. In this case, it shouldn't be too bad, but frequently when you're trying to come up with summation notation, you start just going down all sorts of wormholes, and it can be a real challenge. Now, if that was an important skill later on, I would say, oh yeah, we need to focus on that. But it's not. When you get into differential equations and you're using a general, you're using power series to solve a differential equation, like we've mentioned before, 99% of the time, that power series is not going to be the power series for a common function. So there is no pattern, which means there is no summation notation. And so in differential equations, usually they're just going to say, go out to the 6th order term or something. Go out to the 4th order term. It's not going to be a super important skill to be able to go back and forth between expanded to compact or closed or summation notation, whatever you call it. Lots of different names for it. But here, we should be able to see the pattern, I think. And here, if we're trying to see the pattern, sometimes it's really bad to simplify the coefficients. Simplifying the coefficients just obscures the pattern. But I think in this case, it might make the pattern actually more obvious. So 6 divided by 2 is 3. And then here, 24 divided by 6 is 4. And it's like, oh, okay, this one we can see the pattern pretty easily. So there's our expanded form, and we see, oh, okay, I think we can get at this. So summation notation. So first off, let's make sure that we get a switch in here. So we're going to have a -1. And we need the center to be, I'm going to put a little space for a constant, and the center is going to be at 1. So we need this kind of thing. And if we put a k up here, that k is going to have to start at 0 so that this is gone. The x part is gone for that constant there. Right, when it k is, so we need it to start at 0 so that we can get a constant. Okay, now let's figure out the power on the -1. Should it be a k or should it be a k plus 1?
K plus 1.
Let's see. So if we put k plus 1 here, and then we plug in 0 for k, do we get a positive or a -1 there? So if we plug in 0, we're going to end up with a -1 to the 1, which means we're going to end up with a leading -1. So we don't actually need the plus 1. We only need the k because that's starting at 0. When that starts at 0, -1 to the 0 is +1. So that matches. And when we bump to k equals 1, which would be right here, that'll be negative. Okay? So we don't need a plus 1. Sometimes you do, sometimes you don't. What are we going to put as the coefficient in there then? What's going to go right here? K plus 1. So let's move this over a little bit. And let's put in k plus 1. Let's see if it matches. So when k is 0, this part's gone. Something to the 0 is 1. Here we get a 1. Here we get a +1, so we have 1. Now we plug in k equals 1. K equals 1, we get the negative sign. K equals 1 here gives a 2. X minus 1 to the 1. Plug in a 2. X minus 1 to the 2. 2 plus 1 is 3. even power and -1 is positive. So that is going to be our summation notation, the closed form of this power series. That's the expanded form of the power series. That's the closed form.
I feel like there should be like a reverse sigma at the end or something. Almost like a dx.
What?
Like to close it off, but no.
No. No dx. No dx. Nope. Don't do that. Don't start putting dx's where they don't belong. It's hard enough to get people to write them where they belong. So now that we have the closed form, the summation notation for the power series for f, and so for us in this class, we started with that function. We built this power series. We're going to find the interval of convergence. This function is going to match exactly on the interval of convergence. Okay, so to find the interval of convergence, we are going to use the ratio test, so the interval of convergence. So we take the limit as k goes to infinity of the absolute value of a sub k plus 1. We're taking the ratio of consecutive terms. Ratio of consecutive terms. And we're taking absolute value. If we're taking absolute value, do we need to switch anymore? No. -1 to the k in absolute value is +1. Don't need it. So we're going to have, excuse me, we're going to have k plus 2 multiplied by x minus k to the x minus 1 to the k plus 1. And there could be negatives in there because there's an x. So we still need the absolute on the whole numerator, although we can pull out the k plus 2 at some point. So that's a sub k plus 1. A sub k, divide by a sub k, that's going to give us a k plus 1 times x minus 1 to the k. Let's keep the absolute value on the denominator because there's an x right there. That x could generate a negative value. That's not okay. Now, tell me how many x's are left and where are they?
1 in the numerator.
Everybody agree with 1 in the numerator. So our base is x minus 1. It's raised to the k plus 1 up top, the k down below. K plus 1 minus k is 1. So if we cancel them all out, there's 1 left in the numerator. And x minus 1 has no k in it anymore. The k's are all canceling. So we will just have this, k plus 2. Let's do the numerator. We'll go one more step with the absolute values. The denominator is just k plus 1. Definitely don't need absolute value bars there. There is no k in this x minus 1 factor, so it can come out to the front. Absolute x minus 1 to the front. And then we have the limit of k plus 2 over k plus 1. We have 3 ways to do that limit. Use L'Hopital's, take derivative top, get a 1, derivative bottom, get a 1. 1 over 1 is 1. Divide by the highest power k. Whatever. Cancel out the insignificant terms. Cancel out the k. Limit of 1 is 1. So we know that this limit here is 1. 1 times absolute x minus 1 is absolute x minus 1. So that is the value of the limit. Depends on x. So we know that with the root and the ratio and the geometric series, this value has to be what in order for convergence to happen? Less than 1. So as long as the limit of the ratio of consecutive terms is less than 1, then we have convergence. So now we have to solve this inequality. We will have convergence when this is true. Some of the x's will give us convergence. Some of the x's will give us divergence. So let's see. So this tells us if we expand our compound inequality here, we get that. That's the expansion of our compound inequality. An absolute value inequality is a compound inequality. And we add 1 across. That is the structure of the interval of convergence. We know it's going to go from 0 to 2, but we don't know about the endpoints yet. What we do know is that the radius of convergence is what? The radius of convergence is 1. You can see it in two ways. As soon as you have your x factor that's in the absolute value isolated, your absolute x factor isolated, whatever that number is, that's going to be the radius of convergence. Or you can look at this interval and say, oh, it's 2 units long, cut it in half, radius is 1. So we know that we have absolute convergence for this power series for any number that's between 0 and 2. Between. Now we have to check for the endpoints. So we come over and test each endpoint. So we've got to test the left endpoint, which is 0. So we go to that power series. Again, we don't need to deal with indices here because we don't care where it starts. We just want to know about convergence or divergence now. So it's OK to not put the index in. So we're plugging in 0 for that x right there. So this last factor is negative 1 to the k. So there is our series. Well, we obviously have a couple of common factors there that can be combined. So that's negative
Double
1
switch.
to the 2k. And negative 1 to the 2k,
Is always
always 1. That's always even. That numerator, that whatever it's called, exponent is always even. So this is going to be 1 times k plus 1. So we get that. Maybe I'll put that in parentheses. So what do we think about that series? Converge or diverge? Diverge because? Divergence test. The a sub k does not go to 0. The only way a series can ever converge is if the terms are going to 0 fast. These terms aren't going to 0. So here what we're going to do is say limit of k plus 1 equals infinity, which is not 0. Therefore, diverge by divergence test. Okay, so we now know that the left endpoint is excluded from our interval of convergence. Now we're going to test the right endpoint. So what happens when we plug in a 2 there?
No, 1 to the k.
So 1 to the k, which is just 1, so we don't have any sign to deal with there. And what do we think about this series, converge or diverge? So this is going to diverge also. And once again, it's got the exact same limit as above. So k plus 1 right there. This is a sub k. This is alternating, right? For an alternating series, this is a sub k. So once again, the limit of a sub k is not equal to 0. Therefore, it diverges by the divergence test. The limit of a sub k is not 0. Divergence. So our conclusion here is that therefore the IOC does not include any endpoints. So that is our interval of convergence for that power series. Ready? Break. Let's take 10. And I will go check that video file for you.
Okay.
Let's see why. Oh, the power series.
Whatever matters, like, that's a chance.
All right, let's go ahead and do another one. once again, we see that it's not centered at 0, so we know we have to construct it. No. It's 2431. Not 2430. So 2430 is just online. 2431 is the one that's in the class.
Isn't that engineering?
Yep. They're the same class. Yeah, they're the same class.
Yes, you did.
So again, this center is not 0, so we know we can't just take one of those 12 known power series and fiddle with it. So we're going to construct it, so we have to start taking derivatives. So we're going to do exactly like we did on the last one. We want to get down to the third derivative. And once we get to the third derivative, we can start building. So that is going to be the set of derivatives that we need. 4 non-zero terms corresponds to 3 derivatives. Then we evaluate each of the derivatives at the center. The center of this power series is pi over 4. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4, same thing. On down the line. Okay, so there is the function and the derivative values. Now we can build. Now we can go ahead and build our Taylor series. So again, let's call it T of x for Taylor series. Start with the first constant. And then we get to the second constant and multiply by x minus the center. And then we get to the third constant. And we get x minus the center squared divided by 2 factorial. Put that 2 factorial in the denominator of the root 2 over 2. And our final term, root 2 divided by 2 times 3 factorial times x minus pi divided by 4, quantity cubed, plus dot, dot, dot. So that is our Taylor series. Yeah?
And then on the test, all we'd have to do is this, find the interval of convergence and endpoint.
Well, on the test, you only can find the interval of convergence if you turn it into a closed form, and I'm not going to ask you to do that.
Okay.
So anything I ask you to find the interval of convergence for, I'll give you the power series in closed form.
All right.
But this one,
So this is all we'll do on the test?
on the test, you would just do that, yeah. And I think, though, that it's pretty straightforward in this case. So square root of 2 over 2. We need a little factor there, and then it's going to be x minus pi divided by 4 to the, we'll check in a minute. Looks like k will start at 0. And what do we see in here? 1 over k factorial. Does that look right? Oh, we need a switch too. Oh, no switch?
I don't think so.
Oh, it's funky. It's funky, right? Because we would have to build a switch that's plus, plus, minus, minus, plus, plus, minus, minus, plus. Let's not write the infinite series in closed form here. I'm not going to ask you to do that on the test. This is going to take more work than
I
it.
was about to ask you, how are we going to do the
Yeah.
pluses and the
I thought I heard somebody say, oh, that's easy. Let's see the coefficients. And I said, okay, well, let's write it down. But it's not easy, actually. Because we'd have to have plus, plus, minus, minus.
say, I was
You know
like,
how you said this
How do you
unit?
set up plus?
What?
You know how you said this unit? It's like, I get it, I know.
Yeah.
I know.
That's the bummer.
I think mine's been quite the opposite, actually.
I don't.
It all of a sudden, no single piece is that hard.
I don't understand.
But all we're doing is the same thing we did last week with the Taylor polynomials, right?
Like, if you
No,
let it-
dot, dot, dot.
Part 9, I feel like you did like 50.
I got a 95.
That's true. That one example is hard. That one's the hardest one. Okay, let's
I thought it was
now look at this. So here's a Maclaurin series. We know it's a Maclaurin series because the center is at 0. And whenever we're asked to find a Maclaurin series, most of the time we are going to be taking something we already know and massaging it. And so here, this is pretty simple. Here is our one that's going to be on the test. E to the x is one you have to know, x to the k over k factorial. And this one is pretty simple because all we're going to do is do what with the x? Make it into a negative x, right? So we have e to the x here. This is known. If we want a power series for e to the negative x, all we're going to do is replace x with negative x. So we go to the power series for e to the x, replace x with negative x, and that gives us the power series, more correctly, the Maclaurin series for e to the negative x. And now we should simplify that a little bit. So we've got that. Now, this original series has an interval of convergence minus infinity is less than x is less than infinity. And if you replace the x with negative x, and then divide by -1, remember that you have to switch the inequalities when you divide by -1, so it turns into the same exact thing, right? But we certainly don't write it from this way, so we switch it to the correct way. So greater than negative infinity, less than infinity. Yeah.
on the, I forgot his name already, but whatever the M guy.
Maclaurin.
Yes. Sounds like McLaren. When we have to do that, are you gonna have us do the summation for that series?
Well, you already have the summation for it.
Yeah, yes, so that's what I'm asking. Are we gonna have to, we're gonna have to change it, correct?
Well, you'll leave it in summation form.
You'll leave it in summation form, but we're gonna edit it so it equals the.
Right. Yeah. So you'll leave it in. So you'll start with it in summation form and leave it in summation form.
Okay.
Yeah. Yeah. So for the Maclaurin series, you're going to have that for you. You're going to have that to go with.
McLaren. series.
The Maclaurin series.
That's just wrong.
Vroom.
So is.
Okay. So here once again, Maclaurin series centered at 0. We have this known power series for cosh of x, which, again, remember that e to the x is built of cosh and sinh. So this is just the even powers of e to the x, just the even powers. And all we're going to do here is a substitution. So f of x is going to be equal to, so our function, all we're doing is replacing x with 3x. So we just have to come into the summation. We can probably do it all at once if we want. If we're replacing that x with 3x, we can pull off the 3. So that x becomes 3x, and then the power goes on to the 3 and it goes on to the x. So there it is. Now we have to do the same thing over here. So our interval started out like this, but then we replace the x with 3x. And does that have any effect in the end? No. If we divide everything by 3, we end up with the same exact interval. Infinity divided by 3 is still infinity. So that is going to be our IOC. And there is our summation notation for that. Okay, so both those, when you are centered at 0, usually you can use something you already know. So here's where example on the exam, if you're asked to find, sine of something or e to something, you need to know those so that you can do that. So make sure you know those 5, including their summation notation.
On the test, will you say if like we need to integrate or?
No, I'll just say using. So I'll say find the power series for f using the power series for g, and g is equal to summation. So then you'll have to figure out whether you should integrate or differentiate.
Because if we get f of x and g of x, we should know that we're gonna have to use.
Yeah, exactly. A derivative or an integral. Yeah. All right.
If the interval is infinity, do we even have to check?
I mean, you have to at least say what the new interval is, even if it's the same.
Or will it ever change?
Yes. If the original one is minus infinity to infinity, your question is, can that somehow be reduced? I think that's what can it be changed? And I said yes immediately because I feel like it can, but now I can't think of a good example. That's a good question. I think it can change, though. Pretty sure. Let me think if I can find an example. We always have to check, though, just to make sure. But that's a good question. If it's starting out as the whole real line, what would happen to, because the ones we've really seen change are the ones that already had endpoints. I got to think about that. That's a great question. Okay, so natural log of x. Oh, that center is not 0. No Maclaurin here. So that means we have to do the work. That means we have to take the derivatives. That means we have to plug in the center. That means we know what to do at least. It's procedural, right? Procedural, we like procedure. You're math kids. You like procedure. It would not be cool to come across math students that didn't like procedure. Okay, so if we go to 4 non-zero terms, we're looking at that. So hopefully you've done enough of these that you're remembering this pattern pretty well. Reminder, worksheets due Thursday night by midnight. Reminder, I probably won't be grading Thursday night at midnight. So I probably, oh, that's tonight. So I probably won't even look at it until tomorrow morning at the earliest. So if you're working late into the night, like a good math student, you're probably good to go. Oh, we had some fractional things here.
Yay, gotta love fractional being.
Fractional, some eats.
Would it be would it be easier to have
Easier?
e to -1 and e to -2?
Yeah, you could write it like that. Sure, doesn't matter. Whatever floats your boat. So 1 plus an e times x minus e. So those are our first 2 terms. That's also known as the tangent line, aka tangent line. Minus 1 over e squared times 2 factorial times x minus e to the 2. Hopefully this pattern is seeming pretty straightforward by now. Then we're going to go plus 2 divided by e raised to the 3rd power multiplied by 3 factorial times x minus e to the 3 plus dot, dot, dot. It's a series. It's a series. So there it is. Lovely. Never ending. Math that keeps on giving.
The triple dot is also called an ellipse, right?
Mm-hmm. An ellipsis, I think. What's that? Is that ink? All right, any questions on the terms, the pattern? All right, here's another one. Another exponential looking thing. So
Wait, I have a question.
Too late. All right, what's your question?
Exam. Will you tell us whether like we should like look for a summation form, or do we have to?
I will tell you if you need to write it in summation form, yeah.
Okay.
Yep. So what is the derivative here of 10 to the x?
ln 10.
Oh, yeah.
10 to the x ln 10. 10 to the x ln 10. All right. Y double prime, ln 10 is just a constant, so we really are just differentiating 10 to the x again and multiplying it by ln 10. So we're going to get ln 10 squared. And then we differentiate again. Ln 10 squared is a constant, so it just comes down. And then the derivative of 10 to the x is 10 to the x times ln 10, so we end up with another factor of ln 10. So we've got that.
We don't have to do product.
Well, you can do the product rule if you want to do more work. But you're doing the product rule with a function and a constant, and so the derivative of the constant would be 0. Right? So typically we think if we have a constant times a function, we'll just float the constant down and differentiate the function again. Right? But you could use product rule, and it would verify that that rule for constants just floating down is true. We're going to evaluate the function and all these derivatives at the center of this series. The center of the series is at 2. So let's see, it looks like 100 times ln 10. And then 100 times ln 10 squared. And then 100 times ln 10 cubed. All right. So our T of x, our Taylor series pattern, we see it pretty well, I think. So it's 100 plus 100, natural log of 10, multiplied by x minus center, so x minus 2. So there's the tangent line. And then we're going to the new stuff. Here's the calculus 2 part. Ln 10 squared divided by 2 factorial. And then x minus 2 raised to the 2 power. So that's the best quadratic approximation. And then the best cubic approximation. And it's a series, so we need our ellipses. Now that one would be really easy to come up with summation notation for. That one has super simple coefficients, they're all positive. The factorial is always going to match. The power on natural log of 10 matches. They all have 100. So that one would be pretty easy to write in summation notation. All right. We ready for something new and improved?
It's easier, yeah.
It's just interesting. Scary word in math. Scary word in math. Interesting?
What am I looking at?
All right, so back in grade school, or whatever it was called, you learned Pascal's triangle, right?
No.
What?
8th grade or something?
Who didn't learn Pascal's triangle?
Pascal's triangle?
You learned it?
I remember.
Yeah, must be nice.
You didn't have the opportunity to learn Pascal's triangle?
No.
I didn't learn until Calc 1.
Not till Calc 1?
Yes, and
So Pascal's triangle, you add the two numbers above to get the number below. So you just do that, keep on doing that. And this represents the coefficients for a binomial. So this one right here is just a plus b to the 1. A plus b to the 1, you get 1a, 1b. This is a plus b squared right here. These will be the coefficients. A squared plus 2ab plus b squared. This one will be a plus b cubed, etc. So this is how it's normally presented in high school to create the coefficients of a binomial that's raised to a positive integer power.
What do they call the theorem that for Pascal's triangle, if you take the diagonal of any of the numbers and then the number on the opposite diagonal right below it is the summation of the entire diagonal?
I don't know. So if you take this diagonal and add everything up?
Like you take the 1, 2, 3, 4,
Uh-huh.
and then the number right below
Oh,
the
right
4
below
is
is
10,
the
which
10.
is the sum of
Sum
1,
of
2, 3, 4.
those,
What do they
yeah,
call
yeah.
that theorem?
I don't know. It's a good question. And that's 9, 10, that's 5. Yeah.
Because I've heard that called the hockey stick theorem, but there's got to be a better name for it.
Seems like a good name for it.
Pascal's triangle is infinite, right?
Yes.
So that means no matter how many lines I know, I technically know none of it, right?
No, it technically means you know it all.
What?
I'm optimistic. You're a pessimist.
Ha.
Okay, so if we look at this row right here, this row is going to lead us to the coefficients for. Right, this is going to match right there. So those are going to be the coefficients. Now, here's the part that's going to be new. So if you've taken stats, you've already learned about binomial coefficients. If you haven't taken stats, then this might be really new. So notice up here, this is not a fraction. That says p choose 0. This says p choose k. It's not a fraction. There's no fraction bar. This is p choose k. That's how you say that. P choose k. P choose k. In stats, you learn this. If you're dealing with like a bag and you're pulling out random, ping pong balls or whatever, it tells you how many different ways that you can pull them out. So P choose, if you have 5 choose 2, it means how many ways you can pull 2 balls out of a bag of 5. It tells you all the combinations that you can end up with. So the way that you evaluate, the traditional way of looking at P choose K is as follows. I'm going to do it with numbers because this is a little harder to look at there. But if you do something like 7 choose 3, here is the traditional definition right here. P is the upper number, and you would do 7 factorial. 3 is the lower number, so you would do 3 factorial. And then you take the difference, and you would evaluate that. And this will give you the value, the integer value of 7 choose 3. The application would be if you have a bag with 7 balls in it, this will tell you how many ways you can pull 3 balls out of 7.
How do you spell the choose?
CHOOSE.
Okay. Oh, just like it.
Choose.
Oh,
Yeah.
I thought it was like CHU or something like
Well,
that.
we could
Something stupid.
CHEW. 7 choose on 3
So it's
Yeah, just
so
choose.
it's p factorial over k factorial
times
times
P minus
k
K.
factorial.
Yep.
I feel like I've seen that somewhere.
Yeah, you've seen it in stats or some, inclination towards stats. That's where it shows up the most. And so now we've already done this, right? 7 factorial you could write as 7 times 6 times 5 times 4 factorial, right? And so you would then cancel the 4 factorial and you end up with an expression that has no factorial in the numerator. And so what this is going to do is give us a way to generalize the concept of a binomial coefficient. This is our traditional definition of a binomial coefficient. But if we notice that the p minus k part can always be canceled, that's what this is doing. It's saying, oh, let's take P, do repeated subtraction of 1, and we're going to do it so that we have exactly whatever this number is down here, whatever K is, that tells us when to stop. We're going to stop after we've done 3 factors in the numerator. So here, there's going to be K factors in the numerator. That's the 0th, you count, there's 0, 1, 2, all the way down to P minus K plus 1. So that'll give us K factors in that numerator. This is going to be super important because we will be able to generalize the theorem that we're about to look at. So let's make sure we understand how these coefficients work, though. Let's just look at this one. So this coefficient here, we're going to take 5 factorial, 2 factorial, 5 minus 2 is 3 factorial, right? 5 choose 4. 5 choose 4, we do the 5 factorial, we do the 4 factorial, we take the difference and get 1 factorial. And then when we simplify all these, we get the same coefficients that you would get if you used Pascal's triangle. Or if you did long FOIL, if you did FOIL forever, if you're into foiling. So there's just another example of using the summation of the binomial coefficient. Now here is where it gets interesting. Because we changed the definition, we modified the definition so that there was no factorial in the numerator anymore. Right over here, there's no factorial anymore. So all we did was repeated subtraction of 1 until we reached that number of factors. This now gives us an extension for the binomial coefficients where P can be any real number. So now this is not going to have the how many ways can you pull something out of a bag analogy because, right, P is no longer, normally you think of 5 choose 2. So you've got a bag of 5 balls and you're picking out 2. How many ways can you pick those 2 balls out? That analogy does not work here. Right. -1/2 choose 3 has no intuition to it. You can't come up with something that's going to make sense in the real world. But we can define it mathematically. We do repeated subtraction of 1 until we have K factors. And we get a value. Okay, so that is what we're going to do. This is the generalization that's going to be important for us, is that P now can be any real number, and we're going to use this non-factorial definition of the binomial coefficient right there, which is exampled over here, where we have no more factorial in the numerator. We just have repeated subtraction of 1. So now we have repeated subtraction of 1. We get this oddball number. And it's going to lead us to the binomial series. Here comes the binomial series. There it is.
Are you kidding?
Don't look at that.
What?
Look at this. Here I've rewritten it for you because I know your resistance
Yeah, I don't believe that's the same.
to things that look like that.
Keep it. Keep both. Keep both. Keep both.
So this is going to be our simpler form right here. So let's pull that nasty looking thing down again. So all they've done is taken these coefficients. Come on. All they've done is, so these coefficients, those are just these guys down here. Those are just these. That's P choose 2, that's P choose 3. But rewriting it like this makes it look a lot like a series that you're super familiar with by now, called the, so if we call this the BS, the binomial series, it's similar to the GS, the geometric series, where you have powers of x, right? The geometric series has powers of x. The binomial series has powers of x with binomial coefficients, though. Now, the thing that you cannot do at this stage in your mathematical career is this. You cannot find these intervals of convergence yet because that series has no pattern other than this. And there's no way to do a ratio test with these types of patterns. So this interval of convergence, I have to give it to you for a binomial series. You don't know what it is. You can't figure it out yet. It's very complicated to find them.
Where do they even come from?
And so it takes higher math in order to do these. And so what happens is that depending on the p-value, you will have different endpoints from the interval -1 to 1. Okay, but that I'll give you. You don't ever have to think about finding the interval of convergence for a binomial series. You might have to find the interval of convergence if you modify it, but I will give you the interval of convergence. So let's try one of these puppies. So that when you think binomial series, please think of it that way. Think of it as a geometric series-like expansion where the coefficients are just p choose 0, 1, 2, 3, 4, etc. That's the way you should think about a binomial series. That is the way. All right, so let's try a binomial series here. So we want the binomial series for the for this. So 1 plus x to the 1/2. So that's a binomial. Our binomials, mostly we'd like to get them in the form 1 plus x to a power. So this is going to be p, which is 1/2, choose 0, plus p choose 1 times x, plus p choose 2 times x squared. And we're usually going to go out, four non-zero terms is the standard that we usually go out. But it is a series, so it goes on forever. So plus dot, dot, dot. Ellipses. So now we just have to figure out 4 coefficients. So super, very easy patterns, very similar to geometric series. All we do is put the p up there, and then we count 0, 1, 2, 3, 4. Okay, so 1/2 choose 0. 1/2 choose 0. When you do a choose 0, the answer is always 1. When you do 1/2 or any p choose 1, it's always whatever p is. So the first two are going to be instant. So you don't have to do anything special. Like 5 choose 1, if you go back to the ball analogy, is how many ways can you pick one ball out of a bag of 5? 5. You can pick any one of the 5 balls. So p choose k, p choose 1 will always be p. So there we have that. And if you do the numerical definition I showed you earlier, it will work out. Now here we have to do that numerical definition. So we start at 1/2, and then we subtract 1, and then we divide by 2 factorial. So this is 1/2 choose 2. So in the numerator we get minus 1/4, and in the denominator we get 2, so overall we get negative 1/8. So that is our new coefficient here, negative 1/8 x squared. And then similarly for 1/2 choose 3, we start with 1/2 in the numerator, and we do repeated subtraction of 1 until we end up with 3 factors. So we start at 1/2, subtract 1 and get negative 1/2, subtract 1 again, get negative 3/2, and that's our constant. So let's see, what does that turn into? Looks like positive 3/8 divided by 6. So that is 3 divided by 48. Oh, that can be simplified. That's a 16th. So that is going to be this coefficient. So plus 1/16 x cubed plus dot, dot, dot. So there is our infinite series representation of square root 1 plus x.
Sigma notation time?
No, you can't do sigma notation with this. There's no pattern other than binomial coefficients, so that's all you, if you wanted to write sigma notation, you'd have to just use this, which you're not gonna, you can't like make it any prettier than these binomial coefficients right there. So you're not gonna come up with anything better than that. So we just don't do it.
Isn't there a pattern of multiplying by
No.
2?
There's no pattern.
Okay.
There's no pattern other than the binomial pattern. It may feel like there, if you go far enough out, there's no pattern.
So if we kept going, that pattern would break?
Yes.
Okay.
Yeah, that pattern breaks.
It's kind of like the 1, 2, 4, 8, 16, 31 thing.
That thing.
What's that theorem called?
I forget. I don't remember.
It's like why you
I can't
don't-
remember everything.
It's like why you don't trust pattern intuition.
Oh, look at that. There's that.
Just one.
All right, so let's try another one here. So now we're going to go to the -3. So p is now -3. So we're saying that 1 over 1 plus x to the 3. We're trying to find an infinite series representation of that. So our infinite series are, I should be more specific, a power series. Power series. So that means positive integer exponents. All right. So this p-value is -3. So this is going to be -3, choose 0, plus -3, choose 1 times x. No fraction bar. Don't put a fraction bar in there. -3, choose 2 times x squared. So this is the only pattern that you can write. You can only do that pattern, just the binomial coefficient pattern. There's not going to be like a numerical way to do it other than that.
Are we not doing the approximations?
Oh, is there an approximation in the other one?
There's one on the last.
Okay, yeah, let's do it.
After this one?
Yeah, we'll do it on this one. So again, -3, choose 0. Okay, so that's always going to be 1. And if you go to the ball analogy, like 5, choose 0, how many ways can you choose no balls? One way. You don't choose any. Okay, so -5, or 5, choose 0 is 1, because there's only one way to choose 0. It's to not do anything. So same idea here, -3, anything choose 0 will be 1. Anything choose 1 will be p. So those two are automatic. And then we have to go figure out the other ones. So -3, choose 2. We're starting at -3, and we're going to do repeated subtraction of 1 until we get to 2 factors. All right, we're there. So this is going to be 6. So that will be our coefficient right here. So plus 6 x squared. And then we're going to do the same thing with -3, choose 3.
And then how we get that -3 is going to be the exponent, correct? Like, yeah.
The upper number.
Yeah.
Yeah, p. P is the upper number, k is the lower number, so yeah. So we start with whatever p is. So if we want -3, choose 3, we start with -3, we do repeated subtraction by 1 until we get to 3 factors. And then we simplify it. So it looks like the 3 is going to cancel, a 2 is going to cancel. I'm seeing -10. Tell me if you see something else. So that is this is our binomial series. So if you want, you could call this something. You could call this the series b of x if you want. That's the binomial series. So let's go ahead and do the approximation on this. So we are going to identify x. I'm going to stretch this a little bit. So we want to approximate 1 over 1.1 to the 3. So what is going to be x?
0.1.
So if we look, this is 1 plus x. So in the denominator, it's 1 plus
X is
0.1. So the 0.1 is what's being represented by x. So b of 0.1, that's what's representing x. So we would end up, and 0.1 of course is a tenth. So we would do this kind of thing. And if we use 4 non-zero terms, which is what they said to do, is to use the first 4 non-zero terms, then that is going to be our approximation. So we would simplify it, type this all into your calculator and get a fraction. Yeah?
Can you share how you got those coefficients?
These coefficients?
Yeah.
Didn't I show you?
Yes.
So this coefficient here is -3, choose 2. So we start with -3, and we do repeated subtraction of 1 until we get to 2 factors. And then for -3, choose 3, we do repeated subtraction of 1 until we get to 3 factors. That make sense? Alright?
Yeah. I went the wrong way.
Oh, okay. And then, did somebody type this into your code? 3/4 total?
Yeah.
Oh, beautiful. So that is going to be our
Minus
approximation. And type into your calculator this exactly, like 1 divided by 1.1 cubed. What do you get if you do that?
Over 1331.
1,000 over 1331?
Yes. Do you want that decimal part?
Yeah, let's do them both as decimals too.
That is how many decimal places out?
2 decimal places.
Decimal 75.
Let's go to 3. Let's go to 4.
7513.
All right, and then this one, of course, is 0.75. Okay, so our approximation generated with 4 non-zero terms, so B sub 3. If we want to use the same notation that we used for the Taylor polynomials, the third order binomial polynomial, 0.75, and the actual answer is 0.7513, so pretty close. Pretty close with just 4 terms. All right, let's try one more. So the pattern hopefully is making sense that we're going to take this function. So again, this is useful for this is what our calculators are doing. When it sees something like that, it turns it into a series. And then it truncates it and uses a polynomial. But that's what it's doing. So this is going to be a p-value of 2/3, choose 0, plus 2/3, choose 1 times x, plus 2/3, choose 2 times x squared, plus 1, 2, 3, yeah, one more. So 2/3, choose 3 times x cubed, plus etc. So there is our binomial series, and then we just have to figure out those coefficients. We're going to choose 0 things. There's only one way to choose 0 things. Sit on your hands. Now we have to figure out the 2 coefficients down here. And those 2 coefficients, we're going to start with 2/3. And then we're going to subtract 1 until we get to 2 factors. So 2/3, we subtract 1, we get -1/3 divided by 2 factorial. The 2's are going to cancel, so we get -1/9. So -2/9 divided by 2 is -1/9. So -1/9 x squared. Then we're going to do the same thing, except we're going to go one more factor. So we're going to have 2/3 minus 1/3 minus 4/3 over 6, 3 factorial. So repeated subtraction of 1 until you get the right number of factors. So in the numerator, that looks like a positive number now. So I'm seeing 8 in the numerator divided by 27 times 1 over 6. 27 times 1 over 6. I think we can only cancel a 2. So cancel a 2 in the numerator, so then we have 27 times 3. So there's our next coefficient. Plus 4 divided by 81 times x cubed plus etc. So there is our binomial expansion. We call it v sub 3 if we wanted to. And now they're saying, okay, approximate 1.02. So what's playing the role of x? 0.02. So then all we're going to do is plug in 0.02 into these 4 non-zero terms. And then we're going to type that all into our calculator and get a decimal approximated to 4 decimal places. Whatever we happen to get, that's our approximation. Any questions on generating terms, coefficients, binomial coefficients? Once you've done a few of them, it feels kind of like just not too crazy of a pattern. Did you get a decimal yet?
I messed up, sorry.
Oh, that's all right. It doesn't matter. You guys know how to type that in.
1.617.
Say again?
1.617.
1.617. Thank you. And what about if we did that into the calculator? 1.02 raised to the 2/3 power.
Give it something else.
Oh. You got different than 1.617?
Yeah, I was getting 1.013.
Wouldn't it be two? Wait. Would it be
What did you get when you typed this in 1.02 to the 2/3?
To the 2/3 is roughly 1.013.
Yeah, I think that one must be off then. Did you try it again? You can try it later, it doesn't matter. You know how to type that in. That's going to be the approximation. If you don't type it in correctly, you might lose a point.
And this is going to be like something similar to this as on the test.
Yeah.
Nothing, it is.
Nope, something like that. Something like that. Okay, let's go to our last page in this section. So we've got 2 more that we're going to do. So this is another possibility for the test right here. So that would be the numerical approximation one that we just did. So here we're given a power series already. We actually found that power series earlier. Right? Found that one for the square root. Now this is saying, so this is a subtlety here, this is saying find the Maclaurin series. So Maclaurin series, we're trying to find the Maclaurin series for this. Any idea how we can rewrite this so that we can find the Maclaurin series? Using what's above. Something we've already done a bunch.
We resubstituted like x minus 3 for x. Or...
That's a good question. So if you were to do this, if you were to write this as that, let's see. I want to. Wait, I didn't do that right. You know, you said x minus 3. This is, I think, what you meant. If you force that to be a 1.
Yeah, sorry.
Then So tell me this, is this a Maclaurin series?
No, it's not centered at 0. Right? It's centered at negative. It's centered
Right,
at
so
negative
this is
3.
not a Maclaurin series. That's centered at -3.
Okay.
So that subtraction technique does create a new infinite series for sure, but it's just not a Maclaurin series. So we have to do something that we did way back when we were doing integration with trigonometric substitution.
Oh no.
We factored, how do we force out to be a 1?
Oh, X over 2.
So we factor out the 4, and that's going to leave x divided by 2. Wait,
It'd be X.
x over 4.
Sorry.
Yeah.
I said X over 2 because I was thinking
Of what we were doing with the square.
Yeah.
So does everybody agree with that? So we packed a 4 pulls through the root sign, turning into a 2. There was no 4 with this x, so we're thinking about multiplying it by 1. And now we are going to be able to build a Maclaurin series. So it's going to be 2 multiplied by the infinite series. Let's see. So all we're doing is replacing x with x divided by 4. So it's going to be x over 8. Replace that x with x over 4, so it's going to be 16 in the denominator. So 16 times 8. 16 times 8 is 80 plus 48, 228. I'm starting to get sleepy, so check that. Plug in x over 4 here, so we're going to have 4 times 4 times 4, which is 60.
It's 128.
It's 128, thank you. And then what's this next one? We're going to do 4 cubed, so it's 64 times 16, so 649, 1024. Ooh. So that is our Maclaurin series for that. Question, Jose?
What? Is 16 cubed? Wait, I'll go back.
So we plug x over 4 in here, so 4 cubed is 64. 4 times 4 is 16, times 4 is 64. 64 times 16 is that, which actually makes sense because it's 2 to the 4 times 2 to the 6, which is 2 to the 9.
So then can you factor in the 2?
You could do that if you want. You could distribute the 2. What about this one? What are we going to replace x with here?
You need to test conversions.
Nope, we already have convergence. Oh, but, good point. We're not testing convergence. We're already given the interval, but we do have to modify the interval whenever we do a substitution. Yeah, thank you. So here's our original IOC. So if we replace x with x over 4, great point. So our new interval of convergence is going to be that. So our interval of convergence will go from -4 to 4.
So you replace x with x over something that has a really big denominator, you can make
The
the
interval
interval of convergence
much bigger?
much bigger.
Yes, that is true. So here, the -4x is what's going to go in for x. So this is going to be 1 minus 2x. And again, we're plugging in 4. So -4x goes into there. So 4 times 4 is 16. 16 over 8 is 2. So that's going to be plus 2x squared. And then it's going to go in there. And so we're going to get, what, positive, no, negative 4x cubed. Plus etc. Okay, that's divide right, so that's 4 divided by 2, that's 16 divided by 8, and that's just a -4 left over. Okay. And then we do the same thing that we just talked about, so -1 less than or equal to, we replaced x with -4x. So in the other direction, now we're going to shrink the interval, because we're going to divide everything by 4 here. Change the inequality symbol, because it's actually -4 that we're dividing by. So for this one, the interval of convergence will be -1/4 to 1/4, including the endpoints. Question?
What'd you do for 54?
Let's see. 54. Where's the 54?
problem you're working.
Oh, number 54, sorry, I thought I was looking at a coefficient. So I took the negative 4x and put it in for x. So negative 4 divided by 2 is negative 2. Negative 4 squared. Oh, why is that one not negative? This should be negative. Is that what you were looking at?
Just, you can put in the negative 4x directly.
Yes. So we should be plugging in the negative 4 directly into that x. So negative 4x into there. That gives negative 2. This should stay negative, though, because that's an even power. So the 4 squared is 16 divided by 8 is 2. And then the negative here, we have an odd power, so it's going to stay negative. But it's 4 times 4 times 4 in the top. The bottom is 4 times 4, so 16's cancel, we're left with 4.
How is this related to binomial series?
These are binomial series. So we start with this. This is a root binomial series, and then we're modifying it by substituting. So they are still binomial series.
And will we have to know another one other than this root one?
This one? Well, you'll construct other ones. Like I might give you 1 plus x to the negative 4 or something.
So are you telling us just to know how to build a binomial?
Yes, how to build the binomial
Okay,
series.
so that's just something that we need to, that's what that means up there.
Yeah, that's what that means there. So be able to build this from that. So the coefficients like we did on the last 2 slides. Yeah.
When it's a McLaren series.
Yes.
Okay.
Yes.
Yeah.
A Maclaurin series.
Almost said.
So one of the cool applications that we get with infinite series is that you can just treat them like regular functions. So when you're evaluating limits, this limit that you did in Calc 1, which you used, most likely you started out with L'Hopital's rule, right? That as x goes to 0, you get the indeterminate form 0 over 0. And so anytime you have an indeterminate form of that nature, you could just take derivatives. But once you get into the groove of using infinite series, you can also just use infinite series. So here is the infinite series for sine, which is just the odd powers from e to the x with a switch. Odd powers from e to the x with a switch. Take the limit as x goes to 0. Okay. Well, right here we're still in indeterminate form. But if we distribute this x into the numerator, x divided by x is 1. X into x cubed gives x squared, etc. Now we can plug in the 0 and we get a limit value of 1. So this section is just dealing with these applications where you can just use the corresponding infinite series instead of some other limit technique. So let's look at this one. So here again you get an indeterminate form. You could use L'Hopital if you wanted. But let's do it with an infinite series because that's more interesting. So this is going to be the limit. If we take that power series for inverse tangent, so there's the power series for inverse tangent right there. So we have x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7, etc. So there's our power series for arctan. And then we're going to subtract off x. We're going to divide by x cubed. And when we subtract off the x, don't these just cancel? Those just cancel. Now we can actually divide that x cubed in the bottom into the top and be left with a constant in the first position. So this will be negative 1/3 in the first position. It's going to go in there, wiping out 3, leaving 2. So we're going to have x squared divided by 5. And then here it's going to leave 4 in the numerator. So x to the 4th over 7 plus etc. They're indestructible. And we're taking a limit as x goes to 0. So the whole tail cancels and the only non-zero term is that first term. So there's our limit.
Since that's an intermediary step, we don't need to say what the limit is.
right here. The
Next,
limit, yeah, you don't have, if you've already established it there, you don't have to put it there. That's fine. And then we get to Austin's bow tie.
Bounded by x and native x.
There's your bow tie function. The limit as x goes to 0 is 0, but we're taking the limit at infinity, so we're looking at the horizontal asymptotes. So once again, all right, well, we can use an infinite series, so we can take the limit as x goes to infinity, and this is going to be x multiplied by sine of 1 over x. So if this is sine of x, how do we make it sine of 1 over x? Turn all these x's into 1 over x. We take the reciprocal of each of those x's. So sine of 1 over x, we just come in here and turn all these into 1 over x. So that's going to be a 1 over x right there. This is going to be 3 factorial times x cubed in the denominator. So we're just going to do this all the way across the board. 5 factorial times x to the 5. And then minus 1 over 7 factorial x to the 7 plus etc. So this will be equal to the limit of, if we distribute this x, don't we end up with a bunch of denominators that are going to create fraction values of 0? So that's going to be our limit. So we distribute that x, and then this limit as x goes to infinity, all of the terms other than the first term, they're all going to 0. So then our limit is 1. Voila! The bow tie function. OG. So anytime you see a limit now,
Oh no.
grab that power series, put it in. Who needs L'Hopital's rule?
L'Hopital's is so much faster.
I don't like it. L'Hopital's is so cool and slick. That's like a katana.
Exactly.
It's like chopping a pumpkin in half.
Like, you can still do the limit with Taylor series. It's just like you're trying to, like, cut a cake with a saw. Just use
It's
a
like trying to cut a cake with a saw. I like that.
I just don't know why you would do that.
Yeah, it's like
You've never eaten cake off a saw?
Have you? You just like, I'm not
Jose
talking.
uses an axe cutting up his cake.
No, axe is when it's fancy, when I have visits.
When you have guests.
Yeah, when I'm feeling primal, I bust out the hands.
Bust out the handsaw. Bust out the 3-saw. Bring out the sawzall.
I make sure there's like sawdust in it too.
Yeah.
Like all the people with the
Little flavors.
katanas. Like, oh, so you invited a fake man to
It's usually good.
oh,
It's usually pretty good.
cut something.
Because usually by this point in the semester we've lost some people that probably wouldn't do as
I
well.
don't think it'll like kind of memorize all this. It's like, you have to like,
Practice.
do it with one motion.
But you're not memorizing.
You know the 5 series?
Yes.
Do I memorize the?
Yeah, it sounds
Thank
you, Mr. Boss.
Hey, have a good weekend.
Do I memorize Taylor series?
Oh,
part or
dude,
the
I
summation?
This, I mean, really, you should do both because the